Hi there, I'm James Doss-Gollin. I'm an assistant professor in civil and environmental engineering here at Rice University in Houston, and I want to give a brief overview of some of the things my group is doing trying to identify ways to build adaptive and resilient infrastructure services. So the big question that gets me out of bed in the morning is how can we identify strategies for managing climate risks that are effective, that are equitable, and that are robust to uncertainty? So what might this look like in a perfect world? Let's say we're walking along the beach one day, we find a lamp on the ground, we pick it up, we rub it, out comes a genie. And of course, we get 3 wishes. My first wish is going to be for my soccer team, AS Roma, to start doing a little bit better. But that leaves me with 2 more wishes. So I'm going to wish for unlimited computing and for a perfect global climate model. So we could use this climate model to generate sequences of future weather and run that into a hydrologic or hydrodynamic model that could tell us something like where flooding happens, whose houses are flooded, what critical infrastructure is flooded. We could then look at lots of different interventions, things like green infrastructure, gray infrastructure, buyouts, all these different tools we could use to mitigate flooding. And we could plug those into some kind of optimization framework to identify the strategies that perform the best. And then we could check for robustness by using tools from decision making under deep uncertainty and making sure that the solutions we're finding and optimizing perform well under lots of different possible futures. So this is a nice strategy. Unfortunately, genies are imaginary. Unlimited computing is imaginary. Climate models that we want to work with, while very useful, have serious biases and limitations. The hydrologic and hydrodynamic models, or more generally the local infrastructure and impact models, have lots of unknowable parameters and their own limitations. The mathematical formulation of how to optimize things turns out to have a very large search space, so these problems can become intractable. And again, we have deep uncertainty, which means that there are certain things that we just can't quantify objectively. We have to make subjective choices no matter how good our models are, and trying to reckon with that when it can matter a lot for our decision-making processes is quite a challenge. So with all of these different methodological challenges, it's no surprise that we're not doing as well as we need to in terms of climate adaptation. So for example, here's an image of Houston flooding. Here's another example locally from Texas of a grocery store that closed during the February 2021 cold snap. And more generally, here's a figure from NOAA about the billion-dollar weather and climate disasters that we've seen. And the growing numbers of these kinds of billion-dollar disasters reflects both changes in climate, with more extreme events getting more frequent and or severe, and also the changes in growing exposure and vulnerability to extreme events. So given all of these challenges and limitations, a lot of the work that we're doing is trying to link tools for decision making and identifying policies that are effective and equitable and robust under deep uncertainties, all the way down to sort of bottom-up human-centered models that can tell us something about infrastructure services. So there's 3 main pillars that our group's work falls into to try to make this happen. And the first is to try to understand and start to predict structured hydroclimate risks. So one project that I worked on in grad school was trying to understand what caused a major flood in Paraguay. And what we see, and this is something we see across many different major floods and other large-scale climate disasters, is that the sort of moistures that flows from oceans to land sinks and river basins where flooding can occur, especially for things that, you've got repeated rainfall over several weeks that lead to major floods. These require highly organized climate patterns that can potentially be identified and used for prediction. A related thing is to try and take some of that insight and plug those into statistical models that tell us about risk. So Yu-Chen Liu, who's a student in our group, has been working on developing models for precipitation probabilities. How likely is it to see precipitation above some threshold by blending together some climate indices and some advanced space-time statistical modeling. And another sort of third related piece of work here is to try to understand what are the things that climate models do really well, how can we leverage those, and what are some of their shortcomings, and how can we compensate for those using data-driven approaches. So this was a project from the Ohio River Basin in the northeastern United States. And we found that the climate model didn't do a very good job of simulating regional extreme precipitation days, which was something we defined as when in the springtime we got rain in lots and lots of parts of the river basin all at once. But it did do a very good job of simulating the climate patterns that go along with these days. So we used climate projections of these large-scale weather patterns, but then related those to a statistical model linking those weather patterns to local rainfall hazard. A second pillar is to develop models of the local response mediated by infrastructure of human impacts to different weather and climate forcing. So one example of that is water distribution systems. We know that if we could add water reuse into systems, we could reduce energy uses for pumping and potentially improve water quality. So Xiangnan Zhou, who's a PhD student in my department, has been leading some work looking at how can you model and do optimization on these systems. The challenge is that if you try to solve the pressure equations on the full water distribution network, it's prohibitively computationally expensive to run lots of optimization. So instead, she developed a backbone framework where we do the optimization on a simplified network that has very similar pressure behavior to the full network. And so that allowed us to do the full optimization and get results that are very comparable to if we've been running the full model. Similarly, Arnold Kazadi, who's a PhD student in computer science here at Rice, is leading some work developing a machine learning model of urban flooding. So this is a surrogate model, which means that we're training it on the outputs of a physical model. And once it's trained, this model is very fast to run. So as this model improves, it's going to unlock lots of flood modeling challenges. And the third related piece here is looking at the supply and adequacy of energy systems. So in particular, looking at energy demand as a function of temperature and looking at periods where we've had energy challenges like February 2021 here in Texas, and trying to assess how likely is it that energy demands at different impacts may occur. The third pillar of our work is looking at the specific metrics and objectives that are used to quantitatively compare and optimize different kinds of adaptation strategies, and especially how can we better think about uncertainty and equity in these metrics. So looking at uncertainty, we know that the way we think about uncertainty really matters a lot. There's typically been two schools of thought. There's been the more probabilistic approaches, and there's been the deep uncertainty approaches that emphasize that there's things we can't know objectively, like how much climate change there will be in the future, or what the pace of technological change will be. As useful as those insights are, they can be difficult to integrate into decision frameworks, and ways to sort of represent those as objectives and metrics make a lot of their own subjective choices. So we've been thinking a lot about how do we combine the best of both worlds. A paper with Klaus Keller tries to look at how can we use a subjective Bayesian lens to combine the best of both approaches and make sure that we're exploring many possible futures, developing robustness, but also using probability language to reason about uncertainty in a self-consistent way. On the equity side, we've been looking at sort of how the way that we operationalize different metrics leads to different kinds of decisions. So this work led by Nathan Geldner, who's a PhD student finishing up at Purdue, looks at if you could allocate some money to household flood risk mitigation in New Orleans, where would it go? And it turns out you get very different places that you would spend money if you try to minimize the dollar value of flood damages or the number of houses that you protect. In a place like New Orleans, this obviously has very clear links to race and income as well. So thinking through these things really carefully matters a lot. And more fundamentally, making sure that as we go off and use quantitative tools to inform climate risk management and decision making, that we're engaging with real people, with social scientists, people on the ground, and affected stakeholders. So as an example, we have a project in El Paso looking at not only how can we use emerging tools and advanced water treatment technologies to improve water security for households, but what kinds of monitoring is needed to make sure that these technological advances are really translating into better outcomes for people. So just to briefly conclude, here are a few of the places where we're particularly interested in developing collaborations. The first is on designing scenario tools for climate risk assessment, and particularly thinking about how do we integrate these scenario analyses into formal decision frameworks. Second is improving techniques for physics-informed machine learning, which again offers a lot of potential to speed up our models while still helping to keep them believable. Looking at ways, sometimes called One Water, to link various components of the urban water cycle to develop things that are more resilient, reliable, and again, equitable and human-centric. And last, really anything related to floods, water, energy, and climate, please reach out.